For the last 4 years, every major AI laboratory on Earth has operated under a single, brutal physical constraint, paying Nvidia an 85% gross margin tax just to serve inference tokens to users. That era just hit an immovable wall. OpenAI has officially published the first live hardware benchmarks and architectural telemetry for Jalapeno, its first custom-designed in-house AI inference accelerator developed in partnership with Broadcom and Celestica. The benchmark data, validated across the independent SemiAnalysis InferenceX suite, is staggering. We are looking at nearly 2 times higher peak work per kilowatt, a 4-fold collapse in interactive decode latency, and a shocking 50 to 100-fold throughput advantage under matched latency constraints against Nvidia's flagship Blackwell GB200 and GB300 systems. Even more unprecedented, OpenAI revealed that the low-level silicon kernels powering this chip were not hand-coded by human compiler engineers. They were synthesized by an internal reinforcement learning model called GPT-Astra, executing up to 1.8 times faster than human-authored C++ and Triton code. In this masterclass, we are breaking down the 3 critical layers you must understand. First, the physical silicon anatomy and how Jalapeno solves the memory wall at 550 watts. Second, the raw semi-analysis telemetry across frontier models like DeepSeek R1 and Kimi K2.5. And third, the 10-gigawatt Broadcom deployment roadmap that is about to trigger a brutal price war across the entire API economy. If you build AI systems, manage compute budgets, or invest in semiconductor infrastructure, what you're about to see changes the arithmetic of the entire industry. To understand why Jalapeno is outperforming general-purpose GPUs, we have to look directly at the physical failure mode of modern LLM inference. In training, your primary objective is raw matrix math throughput. You feed massive dense batches into tensor cores and maximize floating point operations. But in inference, especially autoregressive token generation, the bottleneck completely flips. The compute die spends most of its execution cycles idling, waiting for weights and key-value cache tokens to travel across the memory bus from high-bandwidth memory to on-chip SRAM. Nvidia's GB200 addresses this through sheer brute force, pulling up to 1200 watts per subsystem and relying on external liquid-cooled NVLink switches to synchronize state across GPUs. OpenAI took the opposite architectural approach. Jalapeno is rated at a maximum of 700 watts TDP, with sustained production power running at or below 550 watts. Instead of building a monolithic chip that tries to do everything, OpenAI and Broadcom co-designed a dedicated inference ASIC. They tightly wrapped HBM3E stacks directly against the arithmetic logic units and integrated a large domain deterministic interconnect mesh. This architecture keeps the entire KV cache strictly local to the compute cluster, completely eliminating the cross-chip communication stalls that plague distributed GPU clusters. When a model needs to retrieve past conversational context, the data is already physically sitting on the local bus. This introduces a counterintuitive trap that has quietly cost enterprise cloud providers millions. Throwing more general-purpose GPU compute at inference doesn't solve decode latency if your memory pipeline is bottlenecked by physical distance. This brings us to the most radical revelation in the entire hardware release, the software stack. Custom silicon has historically been a graveyard for tech companies because writing low-level compiler drivers and microcode for non-standard architectures takes hundreds of specialized engineers' years to optimize. But OpenAI bypassed the traditional compiler bottleneck by turning to their own AI. They deployed Codex, powered by GPT-Astra, an internal reasoning and program synthesis model trained specifically on hardware abstract syntax trees, register allocation graphs, and memory scheduling heuristics. When human compiler experts wrote the initial execution kernels for Jalapeno sparse attention and mixture of experts routing layers, the hardware ran efficiently. But when GPT-Astra was given the architectural specification and tasked with autonomously optimizing the instruction pipeline, it generated non-intuitive register packing and asynchronous memory prefetch patterns that human engineers never considered. The benchmark results confirmed that GPT-Astra's AI-generated kernels ran between 1.5 and 1.8 times faster than human expert code on critical attention and MoBlocks. This is a foundational inflection point. For the first time in computing history, an artificial intelligence model has designed and optimized the low-level silicon drivers required to run next-generation frontier intelligence at hyperscale. It creates a closed-loop compounding advantage. Faster chips run larger models, which in turn write faster kernels to run even more complex silicon. Now let's examine the raw telemetry published by Dylan Patel and the hardware engineering team at SemiAnalysis. The InferenceX benchmark suite evaluated Jalapeno head-to-head against Nvidia's top-tier Blackwell systems across 3 distinct frontier architectures. First, on OpenAI's OpenWeight's GPT-OSS 120 billion parameter model, Jalapeno squared off against an Nvidia GB200 operating at 1200 watts. Jalapeno achieved 85,448 mixed tokens per second per kilowatt, compared to just 44,960 on the GB200, delivering a 1.9 times efficiency multiplier. End-to-end user request latency dropped from 1.8 seconds down to 1.03 seconds. Next, they pushed the benchmark to extreme scale using DeepSeek R1 670 billion parameter Mo running in 4-bit precision against Nvidia's upcoming 1400-watt GB300. Jalapeno delivered 19,641 mixed tokens per kilowatt versus 11,781 on GB300, cutting end-to-end latency from 5.99 seconds down to just 1.65 seconds, a 3.6 times reduction in total wait time. Finally, on the 1 trillion parameter K 2.5 Mo, Jalapeno delivered 18,195 mixed tokens per kilowatt against 11,862 on GB300, slashing total latency from 5.31 seconds down to 1.56 seconds. Across every single frontier open architecture, Jalapeno demonstrated a decisive 1.5 to 1.9 times advantage in work per watt efficiency over Nvidia's absolute best silicon. While peak throughput numbers make great headlines, the metric that actually dictates real-world application performance is time between tokens, or TBT. When an autonomous AI agent is running multi-step tool calls, terminal commands, or recursive code generation loops, human perception and agent execution velocity depend entirely on single-user decode speed. If an agent has to wait 20 milliseconds per token across a 4,000-token thought chain, the workflow feels sluggish and fragile. Here is where Jalapeno delivers its most lethal knockout punch. On GPT-OSS 120B, Jalapeno achieved a minimum time between tokens of 0.69 milliseconds, translating to 1,459 tokens per second per user, compared to 1.87 milliseconds or 535 tokens per second on Nvidia GB200. That is a 2.7 times velocity boost. On DeepSeek R1, Jalapeno clocked 1.43 milliseconds per token, or 700 tokens per second, versus 5.9 milliseconds and 169 tokens per second on GB300, a 4.1 times speedup. And when SemiAnalysis measured throughput under matched legacy latency constraints, Jalapeno sustained 53 to 104 times higher total token volume. Because the memory pipeline never stalls on inter-chip communication, you can serve 50 users at the exact same lightning-fast speed where a Blackwell node begins to choke. What does this mean for the macroeconomics of artificial intelligence? Jalapeno is not a retail product that you can purchase off the shelf. It is custom first-party data center silicon built specifically for OpenAI's internal fleet, manufactured with Broadcom, packaged by Celestica, and destined for multi-gigawatt data center expansions starting in late 2026. OpenAI's stated 10-gigawatt roadmap with Broadcom represents an existential realignment for the entire industry. Today, inference compute accounts for roughly 80% of total operational expenditure across frontier AI labs. By cutting the capital expense and power consumption of inference nodes by more than half, OpenAI's marginal cost to serve GPT-5o3 and next-generation autonomous agents drops precipitously. This gives OpenAI the structural margin cushion to trigger an aggressive, sustained price collapse across their public API. Competitors like Anthropic and Google, who rely on commercial cloud, GPU rentals, or broader general-purpose infrastructure, will be forced to match these aggressive token price cuts while absorbing significantly higher underlying power and hardware bills. Furthermore, while OpenAI confirmed they will continue purchasing Nvidia GPUs for frontier training clusters, the multi-billion-dollar inference market is now definitively fragmenting into specialized custom silicon. Here is the tactical blueprint for engineers, founders, and technical leaders navigating this transition. First, prepare your software architectures for hyperfast single-stream token decodes. When interactive agents generate upwards of 700 to 1,500 tokens per second, multi-agent debate protocols, real-time code verification, and synchronous voice interfaces become practically instantaneous. Second, stop over-indexing on raw model parameter size and start optimizing for memory bandwidth-efficient formats like MXFP4 and native Mo routing. The hardware of the next 5 years is designed specifically to reward sparse, localized activation over dense monolithic models. And third, watch the data center power metrics closely. The ultimate constraint on the AI industry is no longer access to capital. It is access to electrical power grids. Accelerators that deliver 85,000 tokens per kilowatt at 550 watts will dominate hyperscale deployments, while 1,200-watt general-purpose cards get relegated strictly to training. Jalapeno is proof that the AI frontier is no longer just about algorithms. It is a full-stack war from silicon lithography and AI-written compilers to multi-gigawatt energy grids. Subscribe to AI Enthusiast for real-time engineering breakdowns of the frontier systems shaping our future.